Good day, everyone. Today we are going to be discussing about preparation and uses of standard curve, and I'm going to explain how you are going to carry out this experiment and report it successfully. So what is a standard curve? Right from the beginning of the experiment, we were discussing of standard curve, calibration curve, absorption spectrum, which I believe by now you must have understood the differences between the two, or similarities if there are any. For standard curve and calibration curve, they actually mean the same thing. I know by now you must have known that. If you are still having difficulties differentiating between absorption spectrum, standard curve, calibration curve, you can always refer back to our previous lectures on spectrophotometry and colorimetry. So briefly, a standard curve is also known as calibration curve. It's a general method. It is used to determine the concentration of an unknown substance in a sample by comparing the unknown to a set of standard samples of known concentration. So you will be given a known concentration whereby you will use that known concentration and varying the concentration so that you can have an absorbance, so that you can plot a graph of absorbance against concentration. So if you have varied the concentration of that non-concentration of that concentration of the non-sample, that is the standard sample. So you vary the concentration so that you have different absorbance, so that you can now use it to plot your standard curve. So if you plot that standard curve, you will be given an unknown sample, so that you can now come and, using the absorbance of that unknown sample, you can now come into that graph of your standard sample and extrapolate the concentration of that unknown. That is exactly what we are going to be doing in this experiment. This experiment is divided into 2 or 3 phases. The first phase is to actually determine to carry out determination of calibration curve, whereby you will use a standard sample to plot a graph of absorbance against concentration, that is your standard curve. And after that, you will also be given an unknown protein sample, whereby you will make serial dilution. That is in the second phase. You make serial dilution of that protein concentration, protein X. Then you now measure the absorbance of that protein X. Then you will determine the concentration, the actual concentration of the protein X. That will be the end of phase 2 of the experiment. Then in phase 3, you will still come back to the first phase, where you have different concentration from your sample that was given to you. You will calculate different concentration of the now your sample, and which you have now measured the absorbance. So you will use the absorbance of the tubes to 1 to 2 and to 5, whereby you will use those absorbance to plot what we call the absorption spectra of the 2 tubes. I will explain how you are going to do that. So now, for the first phase of the experiment, these are the reagents that you are going to be needing. You will be given a standard protein, which is the stock concentration is 10 milligram per mil, and you will also be given biorate reagent. And this biorate reagent is consisting of 3 components. You have the hydrated copper sulfate and sodium hydroxide, and also you have Rochelle salt. This Rochelle salt is also known as sodium potassium hydrate. So please take note of these 3 components that are in the biorate reagent. So for this first phase of the experiment, you will be requiring 6 test tubes, where 1 tube will be will serve as blank, okay, and the rest of the tubes will have various different concentration of your standard. So what you will be doing for tube 1, this table should guide you on what to do. For tube 1, which is going to be your blank, and this blank will consist of all the reagent that you are going to be adding except your analytes. Your analyte, that is what you are going to be measuring. So in this case, your standard protein. You are not going to add your standard protein to your uh, blank tube, okay? But you will add all the other components that you are going to add in the rest of the tube except your standard. So what is the essence of this, or the importance of this blank? This blank is used to actually zero the machine so that you now measure the absorbance, okay? You measure the absorbance. It's more like you are using that blank to zero the machine so that you can now measure the absorbance of your samples. So in tube 1, you will add nothing. You add 0 ml of your standard protein, but you will add 1 ml of water, and you add 4 ml of biorate reagent. That will be total of 5 ml. In tube 2, you will add 0.2 mils of your standard solution, standard protein, and you will add 0.8 mils of water, and you add 4 mils of biorate reagent. In tube 3, you will add 0.4 mil of your standard protein, you add 0.6 mil of water, and you add 4 mils of biorate reagent. So in each of the tubes, you have 4 mils of biorate reagent. What will differ is just the amount of water and also the amount of the protein, the mil volume of the protein you are going to be adding, so that each tube will have now different concentration. Okay, so the last tube will have 1 mil of biorate reagent, 1 mil of your standard protein, 0 mil of water, and 4 mil of biorate reagent. In each case, if you calculate, total volume is 5 mils. Okay, so after you do that, because you are going to be measuring the absorbance and this biorate reagent, you are reacting the biorate reagent which has copper sulfate, okay, which will help now in the protein now has peptide bonds. Also, what you are doing now, you are basically trying to react the component of biorate reagent, usually the copper component from the copper sulfate, now react with the peptide, okay, the peptide bond that is in the protein, so as you have the desired reaction, which can now be measured spectrophotometrically. So what you will do after you add all these components, you are going to incubate. There is an incubation time that will be given to you. Okay, so you allow that. The essence of that incubation period is to allow for the reaction to take place between the biorate and the protein that you have added. So how are you going to carry out the concentration to determine the concentration, that's milligram of the protein, and also you are going to carry out, measure the absorbance of the tubes. Okay, so how do you calculate the concentration of the protein? So, but you remember that you are given 10 milligram per mil of your stock. So if 10 milligram is present in 1 mil of your protein, of 1 mil of solution, how many milligram, that's X, will be present in 0.2 mil? That's for tube 2. Okay, so that tube 2, the amount of the protein will be what? 2 milligram. So you now you record your 2 milligram on that tube 2, while your blank will have 0 milligram because it does not contain any protein. You understand? So for tube 3, you do the same thing. 10 milligram is in 1 mil. How many milligram will be in there is a mistake here. How many milligram will be in is going to be 0.3 mil now. Okay, 10 milligram is in 1 mil. How many milligram will be in 0.3 0.4 rather 0.4 mils. So x milligram will now be equals to 10 times 0.4, which is going to be 4 milligram. Please take note of this correction. I repeated the initial calculation. So for tube 2 is going to be 4 milligram. Okay. For tube 3 is going to be what? 6 milligram. Tube 4 will be 8 milligram, and tube 5 will be tube 6 will be what? 10 milligram. Okay. So after you have measured the milligram of protein that is found there, okay. So what you will do, you now take each of the tube and measure the absorbance at 540 nanometer. So at the end of the day, this is what you have. Okay, this are the concentration of the proteins, and also this is arbitrarily the absorbance from previous experiments that we conducted. So I'm using it as an example for you to understand. If you look at it, you see that as the concentration is increasing, so also the absorbance is increasing. So absorbance is directly proportional to concentration, as you all know that. So, and after that, you are going to come and plot the calibration curve or standard curve, which is a graph of absorbance against concentration. So you plot your absorbance on the x-axis and concentration on the y-axis. So you are expected to see a straight line which will pass through the origin, something like this. So that's the first phase. Now the second phase of the experiment will require you to carry out serial dilution of protein X. In this case, you are going to be provided with a set of test tubes. 5 test tubes will be provided. The first test tube will contain your stock protein X solution, okay? And the second, third, and fourth and fifth tube will now contain different dilutions of the protein X. So what you will do in the first place is to add 1 ml in each of the test tube. Okay, you can add 1 ml in each of the test tube, and then it depends on the amounts that is given to you from the stock. If the stock is not much, like for instance, if it is 2 ml that is given to you, you are not don't use the 2 ml directly. You can use 1 ml. But if it is many, what if it is like 10 mils, you can decide to use 2 mils or 3 mils. But however, how many mils you use, it will now if you use what am I saying? If you use like 3 mils, you should know that the amount of water that you are going to be using is going to be 3 mils. Okay, so what we are going to be using here, we are going to go by 1 mil. So when you measure 1 mil of distilled water and you add it to your test tubes, your test tubes will now, 4 of your test tubes will now contain 1 mil of distilled water. So what you will do, you will transfer 1 mil of your stock protein X solution to the first tube. So that will be a total of how many mils? 1 mil of water, 1 mil of your solution protein X, that will be 2 mils. Okay? Then from that 2 mils that you have now created, after shaking, you mix it very well, you shake and you mix it very well, then you pipette 1 mil from that resulting 2 mil into the next tube. So that the next tube will now be 2 mil and the previous tube will be now 1 mil. Do you understand? So you shake it well, then you take 1 mil again from the tube that you just finished shaking now, okay? Now take 1 mil and you now add it to the next tube. You shake well, mix well, then you take 1 mil and you add it to the final tube. You shake and mix well, then you take 1 mil and you discard. So that is your serial dilution. So the first tube, what you did is you added 1 mil of your stock, 1 mil of distilled water. That will be what? 1/2 dilution. Okay. And the next tube, you have taken 1 mil from this 1/2 dilution and you added it to the second tube or the third tube rather, you are having 1/4 dilution. When you take 1 mil of this 1/4 dilution you added here, you have 1/8 dilution. You take 1 ml of this 1/8 dilution and you add it here, you have 1/16 dilution. So at the end of the day, this table will be your dilution, okay? And you are going to measure the absorbance of these 4 tubes, okay? You are going to carry out the absorbance. You measure the absorbance of these four tubes so that you have the first tube will now be of 1/2 dilution, 1/4 dilution, 1/8 dilution, and 1/16 dilution. So if you look at this, the absorbance from 1/2, this is another previous data that I'm trying to explain so that you understand what is actually happening. The 1/2 dilution is, the absorbance here is 0.16. The 1/4 dilution, which is more diluted than the first one, the absorbance is now decreasing. As so, you look at it as the least absorbance here is from 1/16 dilution because it is more diluted. Okay, because it is what? More diluted, so it is having least absorbance. Because you know, if you are asked now, is Beer-Lambert's law obeyed? Yes, it's obeyed because the absorbance is now directly proportional to the concentration. So how do you calculate the concentration of the protein X from the serial dilution that you just concluded? So if you are to ask, if you are to be asked which of dilution you are going to use. So you are going to use 1/16 dilution. Why? Because it is the most diluted, and Beer-Lambert's law calls for dilute solution. So it means you are going to take 0.09 absorbance to calculate the concentration of the protein. How do you do that? So you have to choose that because it is the most diluted, and you can use that absorbance value, go back to your calibration curve and locate from the absorbance axis where exactly is 0.09. When you locate that 0.09, you now trace it and extrapolate down to the what? To the concentration axis. In that case, this, from what we've gotten, we have 3.5 milligram per mil from this our example that we give. So, but this is not the final concentration of the protein. You remember you cut out serial dilution and you use 1/16 dilution, which has the dilution factor of 16, right? So this is the absorbance you've gotten after the protein was diluted. This is the concentration, sorry, you have gotten from the extrapolation, from the calibration curve. This concentration, it means, is the concentration of the protein after it is diluted 16 times. So what is now the actual concentration will be to multiply by 16, okay? This concentration, 3.5 multiplied by 16, that will be 56 milligram, and that is the actual concentration of the protein. And the last phase of the experiment is to determine the absorption spectra of the 2 tubes. From the first experiment, you have tube 1 to 6, right? Tube 1 is blank, and you have tube 2, you have tube 3, you have tube 4 up to tube 5. So you now take tube 2 and you now take the second tube, okay, and the final tube to sketch the absorption spectra of the 2 tubes. Okay, so this is what you are going to do. You just plot, just sketch absorbance against wavelength in nanometer, and you remember that you measure the absorbance at 540 nanometer, which means that is the wavelength of maximum absorption for this particular protein. So you just use hand, it's just a freehand sketch that you will use. You know, tube 1 is having the least absorbance, so tube 2 will have least absorbance, is now at the bottom, and tube 5, the final tube will now have, which has the highest absorbance, right? Will now have the highest peak. Okay, so this is what you are going to do. So feel free, please. If you have any question, you can always drop a comment, and we'll attend to the questions that you have. Thank you very much. This is the end of the explanation of this lecture video. I hope it's helpful. If you have any question, do not hesitate to ask in the comment section. Thank you.